Namely, we reduced, we proved this quotes mixing by Ashiri lemma that told us that we can bound from above the correlations of two sufficiently nice observables with a quantity that involves the equidistributions under the flow of some transverse curves. And if we could prove that all curves transverse to the flow in some direction equidistribute, so the integral of the function goes to 0, then we can deduce the system is mixing, and if we know how fast these curves equidistribute, then we have upper bounds for mixing. Then we did it for, we showed that if we chose short geodesic arcs, and we push them with the Horocycle flow, they do equidistribute at a rate that matches the rate of equidistribution of well, or at least at best would match the rate of equidistribution of Horocycle orbits. So then the question was, is this optimal? And we discussed the fact that no, some other curves equidistribute faster. So if we were to repeat the same argument with curves that are transverse to the foliation given by geodesic and stable Horocycle, we would get some better rates for mixing. And now I want to show that the rates that you obtain from those, the equidistribution of those curves is the best that you can get. And so I want to discuss Ratner's theorem. So she was, in the 80s, she proved some mixing rates for geodesic flows, from which she deduced also rates of mixing for the Horocycle flows. So I want to present her idea, her argument. Again, I will do it in a slightly simplified setting, but the ideas are all there. I will tell you how to go from what we discussed to the general statement. And actually, we will prove, I mean, we will follow our strategy, but by being a bit more careful, we will prove a statement that is a bit stronger to what you can see if you just read the introduction of our article. So in the first pages, she writes some statement and she just proves upper bound, but today we'll be a bit more careful in all the details, and we will prove something slightly stronger. Okay. So what are we going to do? Once again, we will look at the Casimir operator. So this is our favorite second order differential operator. We saw it a few times. And again, so this was defined by second derivative in the direction of the generator of the rotation subgroup minus second derivative in the direction of the geodesic minus second derivative in the direction of the orthogonal geodesic flow. And I will do some manipulation, namely I will write y in terms of u and r. And so if you, we also did it in lecture 2 for when we were looking at ergodic averages, we can rewrite it in this way, which will be more convenient for what I want to do. Again, you can see this as an exercise if you want. Just rewrite y in terms of u and r, and eventually use the commutational relations of those of your Lie algebra. Okay, so what I want to do, I want to look at C2 functions that again are eigenfunction of the Casimir operator. And this time I also want a C2 function that is also invariant by the rotation subgroup. So that if I take the derivative of f in the direction r, I get 0. And let me take some positive eigenvalues. So if we remind ourselves what we discussed in the first lecture, if you can identify a function that lives on M, which is invariant by R, by the subgroup SO2, you can see it as a function of G quotiented on the left by gamma and on the right by SO2. And this was isomorphic to a hyperbolic surface. So this condition is saying, okay, I don't want my function to live on the unit tangent bundle of the hyperbolic surface. I want it to be independent of the tangent vector, so just live on the surface. And then this condition amounts to say, I want my functions to be an eigenfunction for the Laplacian. Okay, so think of it as an eigenfunction of the Laplacian. Okay, I wrote it. So this is what I said in words. So these two conditions means that I'm considering eigenfunction of the Laplacian on this hyperbolic surface being the quotient of the hyperbolic plane by the action of my discrete subgroup gamma. Okay. So I want to look at the correlations of the function f with itself. So I will, for the moment, okay, to prove mixing, I would need to consider all observables and look at the correlation and try to prove that they converge to zero. Let me focus on trying to understand the self-correlations of eigenfunctions on the Laplacian on M. Okay, and we will prove. We will find an exact behavior for this. I will call this function kt. Okay, so k of t are the correlations of f composed with the Horocycle flow times f. So this is just another complex conjugate. Okay. Okay, and the strategy you will see is the same strategy that we used in the second lecture to prove bounds on the ergodic integrals for Horocycle flow. So let me start. In this case, it's going to be a bit more complicated, but not too much. So let me start by noticing, I will look at this as just a function of time, of t. So first of all, I notice that if I take the derivative with respect to time, okay, I can put it inside the inner product. And here I get the derivative with respect to time of f composed with the flow. So this is just the inner product of the derivative of f with respect to the vector field generating the Horocycle flow composed with f. And this is true for any positive or non-negative j. And I will introduce another function, q of t, which are the correlations of f with the derivative of f in the direction of the geodesic flow composed with the Horocycle flow. And this will be because I will need it for the computation. So maybe I'll write these two definitions here on the board so that once I change the slide, they will be up there in case. So k of t are the correlation of f composed with htf, and q of t are going to be the correlation of the derivative of f in the direction of the geodesic composed with the Horocycle flow times f. This is just to keep them here, so we don't forget. Sorry about that. Okay, so let me do some algebraic manipulation. So recall that I took a function f such that r of f was equal to 0. So I can write that 0 is equal to the inner product of f composed with ht with r of f, because this right-hand side is 0. Okay, but now you notice that I can take this derivative and put it on the other side of the inner product just by changing the sign. So it's Q adjoint operator. Okay, so here I get the derivative in R of the function f composed with ht, with f. So this is the derivative of a composition. So by definition, I can rewrite this as the differential of the time t map of the Horocycle flow applied to the derivatives R to the function f, and then composed with ht. Okay, yeah, pause 1 second in case. So is the first step is clear? So I can take the derivative and put it on the other side, but just by changing the sign. And now here I have the derivative of a composition. So if you want by the chain rule, this is the differential of this operator applied to this vector applied to f composed with the dynamics. And so maybe here is worth making a point. So to find the optimal mixing rate, this is more of a philosophical point, so bear with me. To find the mixing rate using the mixing via shearing argument, we needed to push with the Horocycle flow a vector transverse arcs that were transverse to the geodesic and Horocycle foliation. And this is somehow what we are doing here. Here, if you think of it geometrically, we are taking the vector field R, that is the derivative in the SO2 direction, that is transverse to the geodesic and horocycle foliation, and we are pushing it via the dynamics. So at least maybe mentally, we can think of this this step here as doing this, pushing this transverse direction with the by my dynamics. More of a intuition anyway. So here we are really pushing this derivative with the dynamics. How do we compute this? Well, we go back to lecture 1, where we find that the differential of the time t map of the horocycle flow was given by the adjoint. If I identify tangent space is all with the tangent space at the identity, then this object here was just the adjoint of the element generating of the HT element, which is the multiplication by exponential of t times u applied to R. Okay. So what I have to do to compute this differential, I have to take R and conjugate it, multiply on the left by exponential minus tu, that is the matrix 1 minus t01, and on the right by 1 t01. So it's a computation of matrices. You obtain some matrix. Is a 2 by 2 matrix with 0 trace, and I want to express it in my bases R, X, and U. And if you express the matrix that you see in this basis, you see that you can write it as R minus T times X minus T squared over 2 times U. Okay, so this is another moment where, okay, this is a simple computation, but this is telling me something about the nature of the horocycle flow. So when we say that the horocycle flow is parabolic, one way of interpreting it is saying the action of the horocycle flow on transverse direction is polynomial in time. Okay, so the horocycle flow takes, if you vaguely, if you think of taking 2 points very close in the direction R, composing with the dynamics, this is telling you that they are separating polynomially in time in some sense. Yes?
Is the T same as the sigma squared from your last lecture? Maybe I should ask that later. Sorry.
I don't think so, because there, when there was the sigma square, was still pushing the geodesic. So the fact that here I have a square is, so if instead of R I was pushing the geodesic flow, I would get just X plus TU. And here I get a square term because I'm pushing a vector field that is transverse to X. So this is the incarnation of the parabolicity of the horocycle flow. So if you push vector fields up to time t, you see something that grows polynomial in t, not exponentially, as you would see for, say, the geodesic flow, for example. Okay, so this is a thing to keep in mind. And now we can take this expression and plug it in this term in here. So 0 was equal to this term over here, and I found an expression for this push forward of dHT applied to R. So I get R of F, the first term is R of F, and then minus T XF composed with GT. Sorry, here is a type. All G's should be F. This little G should be F. It was typed in my slides, apologies. So you get minus T times XF composed with HT in a product with F, and then minus T squared over 2 U of F composed with HT, comma F. This first term is 0 again because F is the derivative of F in the direction R is 0. So I'm left with minus T times this in a product over here that I called it Q. So this is what I define Q over there. And this term over here is the derivative of K with respect to time. Does this make sense? So I can write that 0 is equal to minus T times Q of T minus T squared over times K prime of T. Okay. So I just rewritten it dividing by T if I'm taking T to be non-zero, say T greater than 1. Okay, so Q of T is equal to minus k prime of t times t over 2. I can differentiate this equation. So I can also find an expression for q prime. Q prime is the derivative of this guy that, if I do it correctly, is minus 1/2 k prime of t minus t over 2 k double prime of t. Okay, so we need from this, I also found some very rough upper bound that we will need later. So k prime of t, we recall, is this inner product, and q prime of t is this other inner product. So it's the derivative of q. So I add a derivative in the direction u in front. So both these k prime of t and q prime of t, if I apply the Cauchy-Schwarz inequality, I get that these two quantities are uniformly bounded in T. Okay, so k prime of T is definitely bounded by, say, the L2 norm of U of F times the L2 norm of F, that I will just roughly bound it with the C1 norm squared of F. All I care is that k prime of T is uniformly bounded in T. And similarly, q prime of T will be uniformly bounded by the C2 norm of F times the C0 norm of F. Anyway, bounded by some constant. So the second derivative of k, so this term is uniformly bounded, this term is uniformly bounded. So the second derivative of k is going to be 1/t times something uniformly bounded. So it's going to be bounded from above by something that goes like 3/t times a uniform bound. Is that okay? So k prime is uniformly bounded, k double prime decays like 1/t, at least. It will decay even better, but at least like 1/t. Okay, so we'll keep these two equations in mind. And now I will do the same reasoning. So before I started with the correlation of F composed with HT and F, now I redo the same thing with the correlation of X, the derivative of F with respect to X composed with HT and F. I redo the same reasoning once again. So here I get the 0 that comes from this derivative. I do the same steps I did before. I take the R on the other side. I compute this differential. This differential is the same. So I replug the expression I found before. And I obtain this term down here. Is this okay? Just redoing the same thing. Starting, instead of the self-correlation, I do it for Qt, so for these other correlations. I hope this is clear. Okay, so last time there was not this X term, so this first term was 0. So I would like to do something similar. So what do? I want to commute X with R. So to commute X with R, well, I know what it is because I just compute the Lie brackets of these two vector fields. So the Lie bracket of R and X is, you do the computation, is 1/2 times Y. And Y, I can rewrite it as R plus U. And I prefer to use the basis R, X, and U. So I will rewrite Y as R times U. So if now instead of this term, I write X times R plus this term over here, okay? Now this first term is going to be 0 because R of F is 0. Then what am I left with? I have this new term that appears here, and it's going to be 0 again. This term over this term, and this will be a k prime of T. And then the two terms that I had before. Okay. And what is? Well, this is x square of F, x square applied to F composed with HT in a product with F. I leave it as it is. And this is the derivative of Q of T. Okay, so 0 is equal to all this thing together. So what did we prove so far? We have 3 equations. We have an expression for Q of T in terms of the derivative of K, an expression for the derivative of Q prime, the derivative of Q in terms of K prime and K double prime, and then an expression for this inner product over here. And now I use the last ingredient that I haven't used yet. So the fact that I'm assuming that F is an eigenfunction for the Casimir. So since F is an eigenfunction for the Casimir, mu times F I can write it. So from this equation, I can write that mu times k of t. Okay, I can take the mu inside the definition of k. And now instead of mu of f, I write the Casimir applied to f. And now I substitute the expression that I had for the Casimir operator, that is this one over here. So I have the first term, I leave it as it is. The second term corresponds to q of t. And the last term, there is a derivative of f with respect to r. So this term will cancel, and this term with the u square is going to be minus k double prime of t. Does this make sense? So if you see, we are basically doing the same thing we try to do for estimating the ergodic averages for the Horocycle flow. We starting from this condition on f and how the dynamics behave. So I can commute vector fields and push one into the other. We basically managed to find the ODE for the function I'm interested in for k of t, because now instead of q of t, I can face this term over here that only depends on k. And instead of this term over here, I can substitute this term over here. So this I have a k prime, I'm happy. Here I have a q prime, and I substitute this term. So I made the q disappear. And now I have an equation that involves only k and its derivatives. Does this make sense?
Once again, why this last term cancelled out? Sorry.
This one?
Yeah.
Yeah, so I'm still assuming that f is invariant by SO2. So when I take the derivative of f with the direction r, this cancels out. Okay, so I'm left with this one, and I plug everything in, and I find a very nice expression for a nice equation for the k that was the correlation function that I want to understand satisfies. And it's very similar to what I found for the ergodic averages, in the sense that it is a linear ODE. This time the coefficients are non-constant, that depends on t, but it's still in a very nice form. And I put on this side these other two terms, because if I just take the left-hand side and e equal to 0, I know how to solve it. And I want to see this as a non-homogeneous version of the equation, where on the left-hand side, I keep the same thing equal to 0. Because now I can use the estimates that I found before. So recall that k prime was uniformly bounded in t, and now it's divided by t. So it's a big O of 1 over t. And we also proved that k double prime is a big O of 1 over t. So I can think of the right-hand side as something very small. It's a big O of 1 over t. So what we proved is that if f is a C2 function that is invariant by SO2 and is an eigenfunction for the Casimir operator, so if basically if f is an eigenfunction of the Laplacian, then the function k, that are the self-correlations of f composed with the Horocycle flow, satisfy this ODE, where on the right-hand side I have an explicit term, k depends on k prime and k double prime, but I will just think of it as a function that depends on t, that satisfies a uniform upper bound of the form constant times the C2 norm of f, something that goes like t to the minus 1 over t. Does this make sense? And again, I know, well, maybe I remember how to solve it, maybe not. I just ask Wolfram alpha or something, and we can find a solution. So let me again assume that mu is not 1/4, because otherwise the solution will look a bit different, but you can also solve it if mu is 1/4. Anyway, if it's not, just for simplicity, then I can solve my equation exactly. So this nu will be the same nu as for the ergodic averages. It will be basically the square root of 1 minus 4 mu, where I choose it to be either a positive real or a purely imaginary number with positive imaginary part. Then I can write an explicit expression for the solution. So kt is going to be the sum of basically two terms. So the constant C1 and C2 will be given by my initial conditions. And this term grow or decay actually, there should be a minus in one of these two terms, apologies, another typo, sorry. One term will go like t to the minus 1 plus nu, and the other will go like t to the minus 1 minus nu. And then I have these two non-homogeneous terms where that depend on, because my original equation wasn't non-homogeneous. Anyway, I have a good expression for k of t, and again, the constant undetermined by the initial conditions. So recall that t of t, the term, the non-homogeneous term in my ODE, satisfy the uniform upper bound of the form t to the minus 1. So we do the same thing as we did for Horocycle averages. Instead of integrating from 1 to capital T, we integrate, we look at this term and we integrate it from 1 to infinity. So that this term will become now a constant. And the remainder, the error I commit by replacing t with infinity is going to be the integral from t to infinity of the same quantity over here. That is going to be of order t to the minus 1 once I multiply it with this term in front. But I will be integrating from t to infinity r to the minus nu minus 1, something that is bounded by r to the minus nu minus 1 times t to the minus 1 plus nu. The nu cancels out and you're left with a big O of t to the minus 1. So by replacing this with the constant terms and adding the constant C1 appearing in this term over here, notice that this term here and this term here will be will decay faster than t to the minus 1. So what I'm left with is that k of t is going to be t to the minus 1 plus nu divided by 2 nu times some constant factor plus an error of size t to the minus 1. So what we managed to prove, when we managed to prove that if a function is, again, under the same assumptions as before, then there exists a constant that depends only on the function, that was this term in bracket over here, such that the self-correlation of f, the difference between the self-correlation of f and this constant times t to the minus 1 plus nu are bounded above by some constant times t to the minus 1. So in particular, if you just care about an upper bound for the self-correlations of the Horocycle flow, you get the absolute value of the self-correlation is going to be bounded by a term that decays like this fast, minus 1 plus the real part of nu, which is going to be less than 1, a number between, well, less than 1 to 0. Okay, so we not only we proved something even a bit stronger than just an upper bound for the correlation, we proved that they are actually asymptotics to a term that behaves like this, which I think is quite interesting in its own. Okay, but this was a very special function that we chose. So you might ask, what happens for more general functions? So since I haven't given you an exercise yet, I can give you one now. You can try to generalize what we did so far. If you, yes,
an estimate of the speed of correlation from below now or not?
This one, yes.
Okay.
Yeah, the correlation are actually asymptotics to this term. Yeah.
And how it is related to the upper bound which you proved in the previous?
Right. So this term. So if you just look at for an upper bound, you can neglect
mu zero.
Yeah. Nu zero is the real part of nu. It's the same.
Okay.
So this is if you just want an upper bound, this is the upper bound for the mixing. So t to the minus 1 plus mu zero, or the real part of nu.
Okay, so it means that for mu zero you can find mu zero and function f, which is.
So I'm saying that if my function f satisfies this condition, so that
It's a very particular mu0, which is related to nu0.
okay, so imagine that I give you an eigenfunction of the Casimir for this value mu. Then mu here is the square root of 1 minus 4 mu.
Yeah.
So if mu is less than 1/4, then this term is going to be -1 plus the square root of 1 minus 4 mu. If mu is larger than 1/4, then this is going to be just t to the -1.
Ah.
So if your eigenfunction has a very large eigenvalue, then the self-correlation decays like t to the -1.
Okay.
And they are actually asymptotics to t to the -1. In a sense, this also tells us that, so this is the same upper bound that we found up to a logarithmic factor. Maybe this is the same upper bound that we found in the mixing via shearing when we were pushing curves that were transverse to the weak stable leaf of the geodesic flow. And this argument also tells us that we cannot expect anything better because of this condition here. So this is not just an upper bound, this is saying that the correlation do actually tend to this factor here. Okay, I don't know that that is not 0, but I mean, you cannot get anything better than that. You cannot hope for anything better. Does this make sense?
Yeah, yeah.
Okay, this is for very specific functions, right? So eigenfunction of the Casimir and invariant by R. But now I'm claiming, okay, we can actually, if we're willing to work a bit more, we can generalize everything that we did so far by replacing the assumption that R was invariant by SO2 just by asking that F was actually an eigenfunction for this vector field as well. So that if I take the derivative of F in the direction R, I get F multiplied by I, this is I, times N for some integer N.
This is not infinite.
No, sorry, yeah, maybe it's so this is I as in the mathematical constant times N, and it can be any integer, F. So I want F to be an eigenfunction for this vector field R, and I can take also the correlation with any G that satisfies the same condition. And I'm claiming that if you look at what we did so far, okay, sometimes we had something equal to 0, this time you will have something equal to I times N times K of T. But the same proof will go through, it's just it's going to be a bit more tedious. Okay, but same argument will go through and you will find some equation like this. And okay, so this theorem basically is not going to be true just for this function over here, but all functions, all pairs of functions that satisfies this condition. And now I can state Ratner's theorem that says that assume that there exists, well, no, she proved that there exists a mu0 that is going to be the nu associated to the smallest positive nu that you have here. There exists some mu0 such that for any f and g that are sufficiently smooth, and in this case, what do I need? I just need that the third derivative in the direction r of both f and g exists and are continuous. And you can actually even weaken these assumptions a bit more, but I don't want to discuss it. So there is some constant such that the correlations for the Horocycle flow decay like polynomially, like, and where the power is t to the -1 plus nu for all positive. So she proved that Horocycle flow mixes polynomials, and she found this upper bound. And by what we discussed in here, this is going to be optimal. You cannot hope to have anything better than that. Because for these very special functions, this is really an asymptotics.
Is it in the previous theorem way, there's no reference to the average of F? Is it implicit in the fact that it's an eigenvalue of the Casimir operator?
Exactly. So every time F is an eigenfunction with a non-zero eigenvalue, it's going to have a 0 average. Yeah. Constants correspond to the case where Casimir of F equals 0. So
when mu is equal to 0?
So if F is a constant, it's definitely going to satisfy Casimir of F equals 0. So if f is a function that has a positive, okay, then there are also other functions that also satisfy Casimir f equals 0, but if you assume that this condition is satisfied for a positive mu, it's automatically going to have 0 integral. Yes, thank you. This is a good point to make. Okay, so this is the result in full generality that was proved by Ratner, and again, I don't want to discuss the proof, but I'm claiming that once you prove this result for these functions, then the rest is harmonic analysis. So just let me say a couple of words really about how to prove it. Well, you use, as we did also in the case for Horocycle ergodic averages, we use some general fact that tells you that if you have an arbitrary function in L2 of n, you can actually decompose it into a sum of functions that will depend on two parameters, mu and n, where mu is an eigenvalue of the Casimir operator, and n is some integer. It runs over a subset of the integers, and all these functions over here are functions in L2, such that moreover there are eigenfunction of the Casimir and eigenfunction of this of the vector field R, and they are all mutually orthogonal. So the theorem goes by proving the results for all pairs of functions of this type, and this is what I claim. And then you want to glue together all the estimates that you find for these individual functions, and that's where you need some assumption on the regularity of the functions in the direction R. Because, okay, for different mu, these are all going to be orthogonal, and then you want to prove that if the function is sufficiently regular, then the norm of these guys decays sufficiently fast. And then you can glue together all the estimates you find for the individual f mu n. I hope this makes sense. Okay, and this is all I wanted to say about mixing properties of Horocycle flows. So if there are
I knew it's just some subset of the original.
yeah, I mean, it's explicit in the sense that it depends on what the eigenvalue is. So if the eigenvalue is positive, it's going to be all z.
Mm-hmm.
If the eigenvalue is negative, it's going to be just a set of z. But for positive eigenvalue, it's just going to be all z. It's just and yeah, so I'll stop here for this. And sorry, change of the slides. Okay, so now we change topic. We talked extensively about the Horocycle flow, and now I want to talk about time changes. I want to go to the second part of the title of my mini course and talk about smooth time changes of Horocycle flow. Okay, so what I want to do, I want to define what they are, look at their basic properties, and then address the same questions as we did before. So try to prove something about ergodicity and mixing. So maybe I will just say a couple of words. Time changes are a type of perturbations that you can do to a flow, and perhaps is the simplest, one of the simplest types of perturbations you can do. You want to perturb your flow just by keeping the same orbits, but changing the speed at which you perturb these orbits. And so you obtain a flow that is still going to be a smooth flow, but in this case, it's not going to be a homogeneous flow as we talked before. So we kind of, morally, we are kind of, in principle, destroying all the algebraic symmetries that were present for the classical Horocycle flow. And so we want to ask what properties are still there, what properties persist, so that we can, first of all, have more examples of parabolic flows to study, which is we want to build a theory of parabolic dynamics. So the more examples that we have, the better our understanding of generic parabolic system. And at the same time, we can distinguish which properties of the Horocycle flow were coming from the parabolic nature of the Horocycle flow and which properties come from the algebraic setting that we are working with. Okay, so let me tell you what time changes are. Again, I always put this slide just to remind ourselves where we are. I will only look at compact quotients again. And so this is my classical Horocycle flow, and now I want to perturb it. I want to perturb it by keeping the same orbits. So I'm not going to modify the individual orbits, but I'm going to change the speed at which I perturb them. And the speed at which I perturb them is going to be dictated by some function, alpha, that is going to be defined on my space to the positive reals. And I will assume that is normalized so that its average is 1. This is just for convenience. So the time change of the Horocycle flow induced by this function alpha, and I will soon assume some regularity of this function. I assume it's smooth. Maybe see if here I'm writing the smooth flow, I'm implicitly already assuming some smoothness of alpha. It's going to be the smooth flow generated by the vector field, by the perturbed vector field. U was the vector field generating the classical Horocycle flow, and now I'm multiplying it by 1 over alpha. So a picture, this is at least heuristically what is happening. So here you have your vector field U, and here you have your orbits. And now here on the right, you have the modified vector field U alpha, so 1 over alpha times U. So intuitively, if these were your tangent vectors, now you have some tangent vector of different modulus. So that the orbits are going to be the same, but if I look at what happens at transverse segments, so maybe in the standard Horocycle flow, you were seeing like this uniform shearing in some direction, and here you will see something more complicated. The transverse segments it will be more complicated to understand what happens, but orbits are still going to be the same. Okay, maybe we can be a bit more explicit. So since the orbits of my time change, so again, my time change flow, I will put alpha here to denote this is the time change of the Horocycle flow generated by alpha. And this is the unperturbed one. So since the orbits are the same, if I start from a point and I flow for time t under my time change, well, I should be able to reach the same point starting from t, but moving for some other time. Some other time that I call tau that will depend on t and the initial point t. Okay, so this is given just by the fact that the orbits are the same. So what does this function tau satisfy? Well, if I start from a point t and then I move with the Horocycle flow for time tau at t plus r, evaluated at t. So by definition, this is just going to be the flowing with the time change for time t plus r. And since this is a flow, I can rewrite it as h alpha t composed with hr alpha applied to p. This is just by definition of flow. But now I reapply my definition of tau. So this term inside the bracket is going to be h of tau rp applied to p. And h alpha of t applied to this point is going to be h of tau of t applied to the point inside the bracket. Sorry, here there is a typo, there should be no p in here. So h of tau of t, comma, h alpha r of t composed with h tau of rt applied to p. And if I rewrite this, I have that this is equal to h of this sum here applied to p. So this tells me that this term in here and this term in here are the same. Namely, this function tau of p that is telling me how the time is different from the flow and the time change is what is called an additive cycle over the time change. So this means precisely is this condition that if I do tau of t plus r t, again, not P, sorry. This is going to be the sum of these two terms, tau of R at T plus tau of T at the point that I moved for the Horocycle, so for time R. This just by definition. Okay, another way of defining the same, another way of finding what this tau of T of P is, well, it's defined uniquely by this equation. So tau T of P is going to be the only real number such that T is going to be equal to the integral from 0 of tau Tp of the function alpha. Recall that the alpha was appearing in the definition of my time change. 1 over alpha was the rescaling that I do to tangent vectors along the Horocycle for time in R. Okay, let me quickly prove this this lemma. Okay, so this is the equation I know for tau. So orbit of R moving for time R with your time change is going to be moving for time tau in the unperturbed flow. I can differentiate both sides with respect to R. So what do I get? So on the left-hand side, if I differentiate with respect to R, I get the vector field defining my flow. And the vector field defining my flow is 1 over alpha evaluated at the point I am at. So 1 over alpha evaluated at H alpha of R of T times U. So this is the vector field generating this flow. And this is going to be, this is the derivative is going to be equal to the derivative of this guy with respect to R. This is this term here. And by the chain rule, okay, so this is going to be the derivative of tau of R of T with respect to R times the tangent vector generating this flow, which is just U. So this is telling me that the derivative of tau with respect to R is going to be equal to 1 over alpha evaluated at the point H alpha of R at T. Or if you multiply both sides by alpha, you get that 1 is going to be equal to the derivative of tau with respect to R times the value of alpha at the point. Okay, now I can integrate both sides from 0 to T. So on the left-hand side, I just get T. And on the right-hand side, I get this function here integrated from 0 to T. And so here I have alpha along H perturbed with times tau, times the derivative of tau in the R, so I can do a change of variables. And so this is going to be absorbed by the change of variables. And this is just going to be the integral from 0 to tau of Tp of the function alpha along the Horocycle. This makes sense. And the fact that this tau is unique follows from the fact that this alpha is positive, so this type of equation will have at most one solution because fixed T and you have a strictly increasing function, so it will intersect at most once. Does it make sense? Okay, but with this, we can already find some information about this additive cycle. So this is telling me how time is parameterized differently from the unperturbed flow to the time change. And we found a very nice expression involving the ergodic integrals of a function along the Horocycle, so we can use what we found to prove something non-trivial about this additive cocycles. In particular, we can prove that the difference that my time t and the time tau is going to be sublinear. It's going to be bounded by some constant times t to the 1 minus gamma, where this gamma is going to be the same as for the deviation for the ergodic integrals. Okay, so let me prove this proposition. Okay, so I'm living in a compact space. So my function alpha is smooth. So it's going to have and strictly positive, so it's going to have a maximum and a minimum. So it's going to be bounded by some a prime and a prime to the -1. So if I So this was the equation I proved before. So T is the integral from 0 to tau of alpha composed with the Horocycle. So this integral is definitely going to be at least the extreme of integration times lower bound for alpha. So it's going to be at least tau of P over A. It's going to be A prime, and it's going to be at most A prime times T of P. This is the trivial bound I can prove between T and tau. Definitely they're going to be up to a constant. But now I want to prove something stronger. Okay, so what we proved for the ergodic integrals is that if I integrate alpha from 0 to capital T, so recall that alpha was having integral 1. So I have to subtract T times the expected value, which is 1. So the integral from 0 to T of alpha minus T is going to be bounded by a polynomial term. So some constant times T to the 1 minus gamma, where gamma is some positive constant. Okay, so if what we proved in lecture 2, it was that 1 over T, the average of the function alpha will converge to its expected value being 1, at least with the polynomial split, so with T to the minus gamma. So now I'm just multiplying everything by T. In the last slides, I call gamma nu, but it's the same, or nu 0, it's the same number. Okay. So, and this was true every time capital T was at least 1. Okay, so if T is larger than A prime, then tau is going to be at least 1. This is what we proved before. So I can use this inequality over here, where capital T is going to be my tau of TP. So the difference between tau and T, I will rewrite it as the difference between tau of TP, and instead of T, I write my expression that I found for T in the previous lemma. And now to bound this term, I want to use this inequality over here with capital T equal tau. So I get that using this, I get this is bounded by some constant times tau of TP to the 1 minus gamma. And now I use again the fact that tau is definitely at most A prime times T. So I get maybe some other constant over here times T to the 1 minus gamma. So what this is telling me is that in compact spaces, if I do a time change, so if I move for time T with my time change flow, this is going to be like moving with the unperturbed flow for a different time, but the difference of time is going to be sublinear in the in T. Okay, so this was some general introduction to time changes. Hopefully this is clear. And now I want to start talking about ergodicity and mixing, but
You have 2 minutes.
okay, maybe it's a good time to just add their questions about this, or if not, maybe it's a good time to start.
Okay, but if you, so the question about ergodicity is irrelevant because it's ergodic.
Yes, I will.
Okay.
I mean, a priori, it's not clear what the invariant measure. I mean, yeah. Ergodicity, I would say what the invariant measure is, and then we will prove that basically the same bounds for the ergodic averages that we found for the for the standard Horocycle flow will be true also for time changes.
Using this inequality as well, or
No.
other questions? Would you repeat again? I mean, we proved that if it is compact, but maybe something else that I missed. Then the time change has to be sublinear,
Right. So
with respect to T. Right?
yes. So
Yeah.
this tau is the function that is telling me if I start from a point and move for time T with the time change.
But the time change, what is preserving the time change? In something is solving that the time change could not be, I don't know, exponential with respect to t.
Right, so the time change is given by changing your generating vector field by some function.
Okay. If the time change is of this form, then
Yeah, so for me, a time change will always be a perturbation of my flow. Perturbation meaning I perturb the vector field, and how do I perturb the vector field?
in this particular way.
In this particular way. Yes.
And this would linear.
You multiply by real numbers.
Yeah.
On this direct hand side of
Right.
the equation.
The multiplication by this alpha.
Yes, the tangent vector are going to be dilated, or in fact, by some alpha that is going to be, by the fact that I will take alpha to be some at least continuous, there is going to be bounded above and bounded below. And so then this tau is telling me the difference in times, the difference in the parametrizations, if you want, between time change. And this is the general equation that we just proved, relating tau with t, and so this was essentially a relation between tau and t that involves an ergodic integrals for Horocycle. And we estimated what they are in lecture 2, namely this grow sublinear. Well, this minus the expected value will grow. The average of this minus the expected value being 1, the expected value, because at the beginning I took alpha for average 1. Then it grows sublinearly. So I mean, the difference with the average to the expected value is the case like p to the minus gamma. So the difference of the integrals with t is growing at most sublinearly.
So if alpha a different integral, it would be just a constant in front of t.
Yeah, yes, correct. Exactly. And yes, that's it. So
No questions. So thank you.